Hi, good afternoon or good morning, and welcome to this ZP webinar on sensor or potentiostat and screen-printed electrodes. I'll basically just jump straight into it, and just to say that the theme today is really starting with screen-printed electrodes, and I've got a few versions of screen-printed electrodes in front of me. This is our 501 carbon electrode, and this is our hyper-value carbon electrode. So just to kind of say that there will be I'll be using these very shortly, so just kind of hang on for that. And I'm also going to say that I do have a potentiostat in front of me, and I will be doing some live demonstrations very shortly. Anyway, the theme today is with ZP. It's funny because people sometimes ask us about specifications, of the potentiostat. And of course, those are important, but really at ZP, there's actually a philosophy, and the philosophy is this simple: whether you're in academia or you're in startup, there's a lot of startups, and there's also a lot of academic papers, but actually the translation into either viable companies or even the startup companies is actually quite low. And so, of course, everyone is very interested in having an idea, especially in the space of electrochemistry and electrochemical biosensors. Everyone has a kind of an idea, not everyone, but and some, a proportion want to actually take it to market and actually get somewhere with a product and actually have an impact on, in this particular case, I'm kind of showing, a clinician. Now at ZP, what we're kind of saying is, okay, we do actually have a pretty powerful technology. We call it Sensor. It does work with our screen-printed electrodes. I will be doing a demonstration with that very shortly. And it really changes the game when it comes to translation of science into real products. And I'll be going forward with that demonstration, so just hang on for that. All right, so there's a philosophy at Zimmer Peacock, and maybe I use a lot of words. I should just say translation of science, especially the translation of electroanalytical sciences. And we do it through the provision of really good potentiostats that are actually can translate into real world products, and also screen printed electrodes. Now, I'm not going to be talking today about actually a lot of what I'll show today is really point of care diagnostics or point of need testing. I won't be talking about our wearables and our implantables, but that is something that we also do at Zimmer and Peacock as well. So I won't be talking about microneedles. I won't be talking about transdermal sensors. I won't be talking about implantable sensors. I'll really be talking about have a sample, put a sample on a sensor, get a result, dispose of the sensor kind of workflow. Now, when I originally started this slide deck, it was really sort of saying, okay, there's sort of 25,000 papers per annum produced like this, where there's a title, there's authors, there's an introduction, there's an experimental section, there's often raw data, and there's actually a calibration curve. And that is the point. See, there is raw data and there's a calibration curve. Once you've got raw data and a calibration curve in this space of electrochemistry or electroanalytical science, you're really on your way to productization, but people just don't take that last step. And that's what we're going to change today. That paper I've just used as an example is not unique. There's another one that's pretty similar. First one was on chili sensing and the other one's on wine sensing, but they're one of about 25,000 papers per annum that are produced like this. And that number is probably not diminishing, actually. It's probably going up. Now, there is a moment, I think, I'm doing this webinar in August 2025. There really is a reset going on in the world, actually, where for the first time in quite a few years, there are quite a lot of redundancies around the world, including academia. So this number of papers that are being published will actually go down. And in part, maybe those redundancies is because governments and therefore taxpayers are not seeing the return on their investment, because lots of papers, but very few translation of products. And it's only those academics and those groups that actually demonstrate translation that should actually get funded in the future. Why should you care about electrochemical biosensors? I simply just give you sort of one example of, in the end, at Zimmer Peacock, the reason that we use electrochemistry in the first instance, and then screen-printed electrodes in the second instance, is just because it completely has demonstrated itself to be an excellent science when it comes to translating assays. So one of the most measured analytes in the world is glucose. There are hundreds of millions of diabetics per day who are testing their we're testing their blood, and electrochemistry demonstrates that an electrochemical biosensor can be low cost. It demonstrates it can be it can be fast, and it demonstrates low cost also in the hardware as well. So my blood glucose there is 96 milligrams per DL. I only do that demonstration because it's low cost, easy to do, fast, requires very little training, and it demonstrates all the great aspects that electrochemistry has. So the rest of this webinar then is having kind of, I think, shown, look, we don't need another science when it comes to rapid testing. It's electrochemistry. Having somewhat demonstrated that with that quick demo, let me go on and actually share the rest. So at Zimmer Peacock, we're taking that great workflow that glucose sensing has shown us, and now translating it using the Sense It All Potentiostat, because it's low cost, easy to use, and rapid results. The thing that's a really big problem in both startup world and in academia is actually the reproducibility of screen-printed electrodes. They're basically shocking. And at Zimmer Peacock, we make a really big effort to make sure that our screen-printed electrodes are reproducible. If you do not have a reproducible screen-printed electrode, you have no chance of, well, no chance is a strong term. Basically, I could almost say you have no chance of really commercializing it, because you're trying to take care of problems on your product like calibration and stuff, and you don't need to really take care of that as long as you make a reproducible electrode. There's lots of conversations about whether graphene and MaXenes and are the best materials. I'll make a big argument, not big argument, I'll just make a quick statement. Graphite's a good material. It's low cost. It's used in lots of glucose sensors, and when you compare it to things like platinum and gold, it's just such a good option. Platinum and gold, great materials, but platinum and gold, I mean, these are precious metals. These are things that are traded, and so people tie up value and wealth in gold. So when you try to compete with gold as a material, and you've got other people who are speculating with it, then it makes for an expensive material. So don't use gold if you're going to make an electrode. Make an assay. Use carbon. With ZP, our screen-printed electrodes, they have good designs. We're very good at what's called compliance voltage. Some of our competitors make potentiostats, and they actually prefer our screen-printed electrodes. And why? Because actually the designs and the choice of materials are so good that we take care of a problem called compliance voltage that actually some of these low-power potentiostats have. Just FYI, if you do get a ZP screen-printed electrode, make sure you get a connector off us as well. Biggest problem that we sometimes have faced is actually people are using third-party connectors. If you've got a bad connector, then you're going to have high impedance. You've got high impedance, it makes all the data look rubbish, and then you think it's the screen-printed electrode. Let me just do a first experiment here. I'm just going to do a quick experiment using ferricyanide. So I will stop sharing for a second. If I just share my phone for a second. So I've got my phone here. At the moment, it does say cyclic voltammetry. I can easily change between cyclic voltammetry, square wave voltammetry, linear sweep voltammetry, impedance spectroscopy, amperometry, open circuit potentiometry. So this is a potentiostat that is controlled by my phone. What I'm going to do is I'm just going to first of all just take that solution off, and I'm going to put some ferricyanide onto there. So I'm going to grab 50 microliters. So one of the great bonuses of electrochemistry is it does not require large amounts of solution. In fact, if you use screen-printed electrodes actually in the teaching, it really it's a good thing, because it basically reduces the amount of chemicals required, and you can actually reuse screen-printed electrodes. I've just put some ferricyanide onto there. I'm just going to give this ferricyanide, I'm just naming this file, ferricyanide 101. Done. Continue. Whoops a daisy. Was that 101? I put 202, but it doesn't really matter. And I'll just hit start measurement. So I'm just going to do a quick experiment when I'm actually going to do the oxidation and reduction of a ferricyanide solution. So I'm just going to share my screen just so you can sort of see what's going on here. So this potentiostat is being controlled by my phone. You can't actually see it that clearly. If I tilt a little bit, I'm trying to tilt to get the brightness down. But let me describe it. It's being controlled by my phone. My phone's in Bluetooth connection with that potentiostat. On that screen-printed electrode, I got some ferricyanide rather, and I'm just doing the cyclic voltammetry of it. This is a unique potentiostat because when I've actually recorded this data, the data is then going to go up to the cloud. So this is a Bluetooth-enabled potentiostat with cloud backup. It says on my phone, upload complete. Let me put that down for a second. I'm just going to share my screen with you. So we've got a system called Julie, absolutely fantastic, a cloud data management system specifically for electrochemical data. I'm looking for something called Ferry 202. There it is, Ferry 202. So that's gone up to the cloud, and then I will see my data up in the cloud. 1, 2, 3. Whoops. Here goes. So what happens then is the data's up in the cloud, so I can see my my 3 scans up here. I'll just show you something just really quickly. So I just want to kind of show you, where I think a lot of potentiostats kind of fall down, because what they don't allow you to necessarily do is, I just want to find that the height of one of those peaks. And in fact, yeah, I'm just going to go for 50. I'm just going to look at cycle 3 for a second. So just forgive me for a second. So I'm just going to do cycle 3. I'm going to try and find the peak height for cycle 3. So here it goes. So there's cycle 3. I've kind of slightly missed the peak height there, but in fact, I'll slide it just slightly so you can actually see that I have got control on that. So I'll just go 250, have a quick look. So this is a really powerful, because it's basically got a data pipe in the system. There we are. I found the peak height there. That peak height is about 7.799. So I'm just going to try something really quickly. Tools. I want to just fit it to a formula. So I'm just going to give this sensitivity of 2 and an offset of 0. I'm just trying to turn peak height back into millimole concentrations, because I think that's really the kind of, yeah, so if I do that at the moment, it's kind of saying that's a 7.799, that's 3.9 millimoles. Let me just tweak something just real quick. I'm just going to put this as 1.75. Just tweaking it to just try and see if I can get, because I know that the solution I'm testing is actually 5 millimoles concentration. So let's just do that. Yeah, 4.457. So I'll leave it at that for now. The reason I'm doing that is because what stops those 2 papers I was using as an example, what stops them becoming products is actually they finish with a calibration line and they finish with raw signal. This system actually allows you to go from raw signal, put it through a calibration, which is what I was just playing with in the data pipe just then, and turn it into concentration. Clinicians, doctors, clinicians, they're all doctors, nurses, doctors, healthcare workers, food technologists, environmental scientists, process scientists, they do not want peak height or concentration or impedance or anything like this. They actually want often concentration. And that's what this technology allows. It allows me to rapidly go from electrochemical data into something that's kind of meaningful for the real world application. So that was a quick. So what the problem we're actually solving with this technology is a philosophical one, which is you're a startup or you're an academic, you're using startup or academic type potentiostats, and they're basically preventing you from getting to market. Because what you want to do is you want to go from technology readiness level number 1 to or 3. 3 is where most academic research finishes. You want to get to technology readiness level 8 or 9. And governments for years have been trying to solve this problem about translation. What we say rather, is you can overcome the problem of translation by actually using a potentiostat like this. And at the end, I could have just as easily demonstrated Red Bull, but at the end I'll demonstrate a real world application at the end. So you'll see that when I say this potentiostat can make real world applications, I'll show it to you as well. So it's not just a conversation of, it's just not just a conversation, it's actually demonstration as well. Now, the reason we're trying to do this is because the real world problem actually is not science and technology. It's actually when you get to market, this is the product life cycle. When you get to market, you actually find out that people are much more conservative to buy your great new technology that could save lives. So you need to get to market as quickly as possible. There's a chasm when one gets to market, and there's a book by a guy called Jeffrey Moore, it says called Crossing the Chasm. So Zimmer and Pico, we see so many companies spend so many years developing technologies. They need to get onto the market as quickly as possible. That's what they do in the tech industry, but yet in the sensor industry, people take a decade to get there. And when they get there, they find this massive chasm of conservatism which they have to cross in order just to get their market, their product developed. So at Zimmer & Peacock, we're kind of like, no, let's use the Y Combinator model. Take our potentiostat, make an assay that works, find 10 customers, ship it to 10 customers, find 100 customers, ship it to 100 customers. Every time you're getting feedback, ship to 1,000 customers. Too many people spend too much time making. I mean, I just saw somebody the other day, they just won a grant in the UK. They won £75,000. What are they going to do with it? They're going to buy an engineer. Sorry, they're going to hire an engineer so they can make electronics. It's basically sort of putting them backwards because they're about to build electronics. If you want electronics for an electrochemical assay, there's plenty of electronics in the market. It's almost, I'd argue, it's almost become commoditized. So don't waste your time and money reinventing something. I'm biased. Use the Sensi or get on the market, make it happen. Then you can start thinking about your first million customers. Eventually, you will want to, own all that technology yourselves. But the first thing is, if you can't find 10 people to buy your technology, stop. And certainly if you can't find 100 to buy your technology, stop. Too many people spend too much time finding out they never get the first customer, but they'll actually spend millions in the meantime not succeeding in getting one customer. At Zimmer & Peacock, we want people to take our screen-printed electrodes and turn them into biosensors. The way we make these circular electrodes, this is the 501. You can make a nice ion-sensitive electrode out of this. You can make small molecules using enzymes. You can covalently attach antibodies, aptamers, etc. to carbon electrodes. So this is a low-cost platform, especially this 501 circular electrode. It's a good platform for handcrafting some initial biosensors and getting them onto the market. As I say, if you don't use our Sensi or Potentiostat, there's no obligation to. We'd like you to. There is actually a connector on our websites as well that you should get hold of. So don't use our screen-printed electrodes unless you can use one of our connectors. We do have other materials like platinum and gold. It's just I don't want to use platinum and gold because I know that it's never really going to lead to low cost. Sometimes there's some reason for the biochemistry that you have to use platinum and gold, but if you've got a choice, don't. If you're not using ZP Screen-Printed Electrodes, follow ZP Screen-Printed Electrode rules or our electrode rules, because then you can design your own electrodes to go with our potentiostat. So we're not precious about people using their own designs and manufacturing themselves. We just ask people to do it in line with our design rules so that you can fit onto our potentiostat. Just a quick kind of demonstration of the utility of this potentiostat. There's something called the Randall-Sevich equation, which kind of says if you're doing cyclophotometry, the peak height of your, if you've got a redox mediated solution, and in my case, I've got ferricyanide, the oxidation of ferro to ferricyanide, for example, would be proportional to the square root of scan rate. And that's the Randall-Sevich equation. I just want to kind of give you a quick demonstration. Actually, I'm going to take my phone. I'm going to hold it up to this camera. It says that. I'm going to go done. Now it says cyclophotometry. I'm just going to hit this little icon here, because now what it's going to want to do is opens up my camera and it wants to scan a QR code. I'm going to scan that QR code that says Peacock voltammetry. Right, now my phone says Peacock voltammetry. So I'm just going to give you another quick demonstration, just to kind of a lab practical, let's say. So let me just stop sharing that for a second. Let me go down to here. So I've got my wonderful Sensi or Potentiostat. I've got my 501 electrode there. I've got my ferricyanide on there. I've got my test method here. I'll call this Butler, because this is, I'll call this Butler. Right, go continue. This is just to demonstrate to you how we can, we don't need menus and etc. We can control this potentiostat just from QR code. So here I'm doing a sort of classic undergraduate experiment called the Butler-Volmer experiment, where I'm scanning the potential. I get an oxidation in a minute. I'll get the reduction wave. Here comes the reduction. This one is the first scan, and it's going to be quite slow, but then you'll see that I'll do about another 3, and it'll get faster and faster for each one. So that's the first one. Now the second one, going a bit faster. So you can see that we're able to allow people to generate QR codes, which can come up with quite sophisticated experimentation, and all of that gets automated through a QR code. And you're going to see that all this data actually ends up in the cloud with very little involvement from me. And it really helps in teaching. It really helps in automation. But all I'm really demonstrating here is the Butler-Volmer is a very good, it's let's say true, that the peak height is proportional to the scan rate. Now what I'm going to do is I'm just going to share my screen with you for a second. So here it goes, and you'll see that pop up. Yep, there it goes. And I will just change this for a second. Okay, so I'm just going to go up here. Love the fact that every time we do an experiment, it's the data is immediately up here. So just do a quick refresh here. We live in a wonderful moment, actually. I mean, once upon a time, I was talking about Bluetooth and cloud computing and smartphones, and now I have to talk about AI. So we live in a, you could say it's scary, but we live in an amazing time in history. But if I go into here, what I'm going to demonstrate to you now is that just that one QR code, I was able to program that potentiostat. It actually did 4 scans, gathered all the data, sent the data immediately to the cloud, and then also fitted it to what's called the Butler-Volmer. So I can see here that it's done the 4 scans. I'll just zoom in a bit so it looks a bit better. And it's fitted it to a Butler-Volmer, and it kind of says, that, yeah, the signal is proportional to a coefficient here, and x to the half, and x being the scan rate in that particular case. Now, that was a demonstration. That's what I did. I'm just going to give you a real-world example. I'm just going to reach up, because actually, I often, if I'm doing these webinars, I will actually demonstrate caffeine, but I'm actually going to do a bit old school with us today. I'm actually going to demonstrate. I've got a demo shortly with a client testing chilies. So in fact, I'm going to use chilies. So don't forget, I'll hold my phone up for a second. My phone says peacock voltammetry because we were doing a Butler-Volmer analysis. I'm going to scan the QR code for chili now. So I'm going to do that thing again where I go here. My phone's looking to scan a QR code. Now it says chili. So I will, because I scanned that particular QR code there. So now I'll stop that. It does say chili. I will put my phone down here. Just get my chili sample in here. I will prepare it. Everything is live, by the way. Right, so I've done that. Now I will get, have I even got 100 microliter pipette here? No, but I'm just going to grab one. Now I do have 100 microliter pipette. I'm going to grab a tube. So I hope you're enjoying the live element of this. I love electrochemistry. Look how dirty, not dirty is a strong term, but it's not like most analytical sciences where you need these amazingly pure centrifuge filtered samples. It's like, no, you do not need that. I mean, that's why I did that test earlier on my own blood. Electrochemistry is not that kind of science. It's a very robust science. I think I'd actually go as far as saying as an analytical science in the domain of chemistry, biology, biochemistry, I think it's actually the one science that actually can take the dirtiest samples in the world, or the least purified, the least prepared. Now what I'm going to do is I'm going to take that. I'm just going to add some buffer to that. I'll hold the sample up to you so you can see it. There it is. I've just got a vortex. I'm just going to quickly mix that. 1, 2, 3, 4, 5. It just allows me to really just vortex it up quite quickly. Now what I'm going to do is I'm just going to grab one of our screen-printed electrodes. The only reason I'm going to get away with this is because Zimmer & Peacock makes the world's most reproducible screen-printed electrodes. So I'll take one of our electrodes. I will put them in here. I will close that up. I've got my phone here, which is now a chili sensing phone. I'll put Tabasco in here. Tabasco, all very good. I'll go like that. I need to put that sample on here before I forget. Another example of electrochemistry, it can take really easy samples. Sorry, it can take really small samples, 50 microliters, on it goes. Put a 50 microliters on like that. Whoops, a daisy. I go continue, start, It's the same story as before. So you might just notice something actually. This assay is going really quickly. If you're developing electrochemical assays, just go make them quick. The longest assay we actually have is a 4-minute assay. So that says 2,720. That is something that you can verify by looking it up. I was going to say looking up online, but I realize that people, just ask ChatGPT these days. I realize that's gone a bit blurry, but that is the result. What I'll now do is I'm just going to change screens for you for 1 second. Or rather, I'm going to share a screen with you for 1 second. So far we've done a load of experiments, but now what I'm going to do is I'm just going to go report, and I'll just do a quick refresh here. So there it is, Tabasco, great. I'll double click that. And you'll just see the same story as before pop up, that I'll get my data, I can see everything, I've got great traceability. But it just shows you this is a potentiostat. And I started this presentation by saying, oh, here's a paper about measuring chilies. And at the end of it, I actually just did a chili measurement. And that paper, the only thing it really lacked was its translation. It didn't translate into a real product. But you can see that actually in this, we were able to translate that. Beautiful voltammetry for capsaicin here. And we took the last step, which was turning it into something meaningful. In this particular case, about 2,700 Scoville heat units, which also appeared on my phone as well. So you could see that we could send the data back to the phone as well. I might just finish off with as I say, a real world example. I could have just as equally done this on chili as well. So we do have a real, sorry, not chili, Red Bull as well. We do have a real technology stack, which is sensors or screen-printed electrodes, Potentiostat, app, Julie Cloud, and able to send real results back to the phone. So in the end, the theme today is this: plenty of academic research going on, plenty of, quite a few startups, not as many as academics, but a real distinct lack of translation. And the problem being is that so many instruments are really just designed just to do R&D, and the Sensio Potentiostat plus the screen-printed electrodes that we do at Zimmer Pigot absolutely intended to get people to a much higher technology readiness level than has traditionally happened. If you do have any questions, don't hesitate to reach out to us. Okay, thanks very much.